Copper spires and finials are required to be bonded to the grounding electrode system, especially in residential construction. This bonding is crucial for electrical safety and compliance with the National Electrical Code. The grounding electrode system is a network of interconnected grounding electrodes such as ground rods, ground rings, metal water pipes, and building steel, designed to provide a low impedance path for fault current to return to the source. This low impedance path facilitates the rapid operation of overcurrent protective devices such as circuit breakers or fuses in the event of a ground fault. Without proper bonding, metallic components like copper spires or finials can become energized during a fault condition, posing a shock hazard to individuals who may come into contact with them. The purpose of bonding is to ensure that all metallic parts of a building's electrical system are at the same electrical potential, minimizing the risk of electric shock. The NEC specifies requirements for grounding and bonding to protect people and property from electrical hazards. Section 250.104. Covers bonding of metal water piping. Section 250.50 covers grounding electrode system installation. Section 250.52 covers grounding electrodes. Bonding these copper elements prevents them from becoming energized and creating a potential difference between them and other grounded parts. Firstly, understand what a grounding electrode is. A grounding electrode is a conductor that is connected to the earth to provide a low impedance path for fault current. Common types of grounding electrodes include ground rods, metal underground water pipes, and concrete encased electrodes, also known as UFA grounds. Secondly, recognize the role of the grounding electrode system. The grounding electrode system is the interconnected network of all available grounding electrodes at a building. It ensures that all electrodes work together to provide a comprehensive grounding path. Thirdly, consider the purpose of bonding. Bonding is the process of connecting metallic parts to create an electrically conductive path. This path ensures that all bonded parts are at the same electrical potential, reducing the risk of electric shock. Fourthly, identify the specific requirement for copper spires and finials. While the NEC doesn't explicitly mention copper spires or finials, the general requirements for bonding exposed metal parts apply. Any metal part that is likely to become energized must be bonded to the grounding electrode system. Fifthly, evaluate the likelihood of energization. Copper spires and finials, especially those mounted on rooftops or high points of a building, are susceptible to lightning strikes. They can also become energized due to faults in the electrical system or induced voltages from nearby power lines. Sixthly, examine the bonding methods. The typical method for bonding copper spires and finials involves connecting them to the grounding electrode system using a copper conductor. This conductor must be sized appropriately to handle the potential fault current. Seventhly, choose the correct conductor size. The size of the bonding conductor is determined by the size of the service entrance conductors, as specified in NEC Table 250.102. See, this table provides the minimum size of the grounding electrode conductor based on the size of the ungrounded conductors. Eighthly, install the bonding conductor properly. The bonding conductor should be installed in a manner that provides a lower impedance path to ground. Avoid sharp bends or kinks in the conductor, as these can increase impedance and reduce the effectiveness of the grounding system. Ninthly, make secure connections. Ensure that all connections are mechanically strong and electrically conductive. Use appropriate connectors and fittings to make secure connections to the copper spire or finial and to the grounding electrode system. Tenthly, inspect and maintain the grounding system. Regularly inspect the grounding system to ensure that all connections are intact and that the grounding electrodes are in good condition. Repair any damage or deterioration promptly to maintain the effectiveness of the grounding system. To elaborate further, the NEC section on grounding and bonding, specifically Article 250, provides comprehensive requirements for ensuring electrical safety. The primary goal is to create a low impedance path for fault current to return to the source, which facilitates the rapid operation of overcurrent protection devices like circuit breakers and fuses. This rapid operation is essential to prevent electrical shock and minimize damage to equipment. The grounding electrode system is a critical component of the safety mechanism. It typically consists of one or more grounding electrodes, such as ground rods, metal water pipes, or concrete encased electrodes, all interconnected to form a robust grounding network. The purpose of this system is to provide a stable reference point for the electrical system and to dissipate fault current safely into the earth. Bonding, on the other hand, involves connecting all non-current carrying metallic parts of the electrical system to ensure they are at the same electrical potential. This includes metal conduits, enclosures, and other metallic components that could become energized during a fault. By bonding these parts together, the risk of electric shock is significantly reduced. When considering copper spires or finials, their location and composition make them potential targets for lightning strikes or induced voltages. If these metallic elements are not properly bonded to the grounding electrode system, they can become energized and pose a significant safety hazard. The NEC requires that all exposed metal parts that are likely to become energized be bonded to the grounding system. While copper spires and finials may not be explicitly mentioned in the code, the intent is clear that any such exposed metallic elements must be included in the bonding system. The bonding conductor used to connect the copper spire or finial to the grounding electrode system must be sized appropriately to handle the potential fault current. NEC Table 250.102. C provides guidance on selecting the correct conductor size based on the size of the service entrance conductors. This table ensures that the bonding conductor is capable of safely carrying the maximum fault current that could occur. In addition to proper sizing, the bonding conductor must be installed in a manner that minimizes impedance. Sharp bends or kinks in the conductor can increase impedance and reduce the effectiveness of the grounding system. Therefore, it is important to ensure that the conductor is installed as straight as possible and that all connections are secure and electrically conductive. Regular inspection and maintenance of the grounding system are also essential to ensure its continued effectiveness. Over time, connections can corrode or become loose and grounding electrodes can deteriorate. Regular inspections can identify these problems early on, allowing for timely repairs and preventing potential safety hazards. In summary, the requirement to bond copper spires and finials to the grounding electrode system is a critical safety measure that helps protect against electrical shock and equipment damage. By following the guidelines outlined in the NEC and ensuring that all metallic parts are properly bonded, the risk of electrical hazards can be significantly reduced. Residential construction is very much included in this requirement.